Back in about 200 BC, a mathematician named Apollonius showed that by cutting a cone at various angles, you could get the different parabola, ellipse, hyperbola, which is why they're now called the conic sections. And I want to show you how you can do that. Here we have a cone with, I'll make the length of this side 30, this side's also 30, and the base is 18. So these two don't have to be equal, but they are in this case. And I'm going to cut the cone starting so that BD is 10 units long, that's this. And I'm going to make the cut so that this line, the plane that I'm cutting the cone in, is actually parallel to the side of the cone. And Apollonius is going to show that this red curve over here would have to be a parabola. And we can actually find the equation of the parabola using two theorems from geometry. One thing I want you to notice is that if I make this the vertex of my parabola, this green line is kind of like the y value for a point, and this yellow line is kind of like the x value of the point. So I'm going to first show how we can make a relationship between the y value, this line over here, and this value over here that is, I'll call it the z value. Now this circle could be anywhere along the cone, but this is just a generic spot to put it at. So if you take a look carefully, what you'll see, whoops, let me get rid of some of this stuff. Because of this triangle right here, we can say z over y. This triangle is actually similar to the giant triangle that makes the cone. So z corresponds with the 18, and the y corresponds with the side on the right, which is this 30. And if I multiply both sides by y, I get z equals 18 over 30y. I can reduce it to 3/5 y. So now I have an expression for z. Now, if you look at this circle, it's kind of hard to see, so over here is a top view of the circle. There's a property of circles that if you multiply the two pieces of one chord, you'll get the same answer if you multiply the two pieces of the other chord. In other words, x squared is equal to a times z. Now this a value, because of the way I made this cut here, this a value will be the same no matter where my circle is, and that includes this point over here. So on the side, I need to calculate out DE. And I can do that by noticing that this DE is here, and this 10 is part of that triangle, and that triangle is similar to the large triangle also. So I can say DE over 10 is equal to 18 over 30, or DE equals 18 times 10 over 30, which is 6. So this is 6. That means that this is 6 also. This a is a constant, so it's 6z. And then I can replace the z with 3/5 y, and I get 6 times 3/5 y, which is 18 over 5y. Notice how this looks like a parabola equation, especially if I multiply both sides by 5 over 18. Y equals 5 over 18x squared, which is the answer. There's also a way to do this with an ellipse. It's a lot more complicated. That's to be done another time.